Welcome back to the fifth video about our little Melexis MLX90363 Triaxis magnetometer. In the previous video, we talked about the so-called by Melexis trigger modes, all three of them, and of course we also implemented them, including sending some non-standard SPI signals over the slave select line. Card here, link in the description. In this video, we will start to fiddle around with the different configuration options that thing has. And it has quite a lot. But for now, in this video, we will restrain ourselves to just reading out the configuration of that thing. But before that, we do another little bit of housekeeping in our library. Enjoy! So, housekeeping. By the way, it's 31 degrees Celsius again, so I'm a little bit sweaty. Anyway, in part 2, card here, link in the description, we moved two enums into the public part of our library. And these were the enum marker and the enum MISOOpcode. And of course, we had two associated public methods to retrieve the marker and the MISOOpcode from the last message we received from our slave. And I never really liked exposing the marker and the MISOOpcode outside the library. It has too many drawbacks and it's really a hardware-specific detail. I mean, there's two marker bits and 1 byte and then 6 opcode bits, unless they are not opcode bits but roll counter bits. That's I don't want any user of the library to have to mess around with that. And of course it has practical drawbacks. I mean, if you look here in our sketch at our serial print MLX90363 last slave message, we have a two-level switch statement. First, we have to switch over the last marker, and we have to know somehow that if it's a marker other, we have to switch over the last MISOOpcode. So, suboptimal. In the new code, the enum marker and the enum MISOOpcode are private again. And unfortunately, I have to have this little private section before the public section because C++. More specifically, because I have now here an enum class received, which is a flat list of all possible messages we can receive from our slave. So from alpha, alpha, beta, x, y, z, the so-called regular messages, to knob, ready, get 3 ready, standby, error, and T, the so-called other messages. And of course, in the definition of that enum, I'm referencing the marker and the MISOOpcode. And because I'm a lazy guy and don't want to write all the time here marker other and cast that to unsigned integer 8 and binary OR it to the MISOOpcode cast to unsigned integer 8, I have here a macro defined, which I'm using down here. And so it looks nice. I also defined a macro for just the regular messages, which just get a marker as an argument. But I immediately undef these after I defined my received enum. And here's a public method last received to get that enum received, that is the MISO message type we last got from our little slave. That's the implementation of that new method in the CPP file. So first I test if my MISO message, all messages, marker, binary ended with the bit mask marker. Yeah, I introduced some constants for all the bit masks. Okay, I won't go over them, but I moaned about that also in the second part. Is equal to the marker other for other messages. If that's the case, I take the whole MISO message, other messages, marker opcode, and cast that into a received enum and return that. Otherwise, if we have a regular message, I just take MISO message regular, marker roll counter, and binary AND that with a bit mask of the marker, and cast that into a received enum and return it. And of course, the old methods here, last marker and last MISO opcode, we don't need them any longer. And that makes handling receiving messages in our sketch and also in other parts of the code, but I will just show you here the change as an example to our serial print MLX90363 last method much easier, because now I only have one level of switch statement which can handle all the messages there are. Okay? No more two-level switching stuff. Much better. I guess I don't have to mention that this version of the code does exactly the same as the version before. It's just internally much nicer. Let's move on to the real subject of this video, and this is reading out the configuration. And in chapter 15, we find a long list of what Melexis calls end-user programmable items. First thing to note here is that the parameters will be programmed through the EEWrite message. We will talk about that MOSI message in the next video or so. EE stands, of course, for EEPROM. Meaning that whole thing is configured by writing to its EEPROM. And unfortunately, Melexis doesn't provide any lifetime data for the EEPROM, that is, how many write cycles it will survive. The idea here is you have that little chip somewhere in your production line, you do your configuration, and then you're done with EEPROM programming. Our context is, of course, a little bit different from that, but it should survive at least 10,000 write cycles or so. The second thing to note is that it must be noted that the data type of EEWrite message is a word, so 2 bytes, 16 bits, and therefore it is mandatory to first read back the complete contents of the word before changing only the bits corresponding to the parameter. This is really important, and in our context we'll probably read out the whole configuration first before writing it to the chip after changing some parameters. If we have a look at the table of parameters, we can distinguish 2 blocks here. The first block goes from map XYZ to pin filter. And these are really parameters that influence the functionality of the chip. Then we have a second block here, user ID and free. User ID is just the user identification, freely programmable, and free is freely usable memory by the user. And please note that the addresses here are all over the place, and that some parameters just occupy a few bits within an address, while other parameters occupy a whole 16-bit word. And then there are 2 inconsistencies here. First one being SMISM and select SMISM. These are of course 2 parameters. One is occupying 1 bit and the other is occupying 15 bits. Plus the pin filter parameter here is located at address 1001. However, that EEWrite function can only write even addresses. So Yeah, we have to take care of that. Last remark, if you look here at the order of the addresses, they are all over the place. So that's not a memory map, that's more, a list, not even alphabetical, of the parameters and where they reside. We need to do better. The information about ZEL, SM, ISM and SMISM being actually two parameters you find in chapter 16.32, and the whole chapter 16 is basically dedicated to explaining briefly all those parameters. There will be really some experimenting involved to find out what they really do. Anyway, as I mentioned, ZEL, SM, ISM, so select is a single bit, bit 15 in the word 1032, and it switches something on and off or back and forth, whatever. And SM, ISM occupies the other 15 bits, 14 to 0, and represents a float value between 0 and 2. But we have 3 more addresses, and those are mentioned in chapter 14, traceability information, and they contain an 48-bit MLX ID, a traceability, so individual number of each chip, in 3 16-bit words within the EEPROM. Obviously, you shall never write those. Now, you remember I said we have to do better. So I tried to create a proper memory map as an enum class address in the public part of our library. It's of course 16-bit addresses throughout, so it's unsigned int 16. Also, I mentioned that only even EEPROM addresses are writable, so the least significant bit of the address is always 0. So we start here at 0, 2, 4, 6, 8, then 20, that's undocumented, 2, 4, 6, 8, 30 is undocumented again, and so on. And here's my personal memory map of that thing's EEPROM. So we start with that pin filter word that contains the pin filter. Bits 7 to 0 are undocumented. 9 to 8 are actually the pin filter parameter, and 10 to 15 are undocumented again. And remember, in the datasheet, it was located at address 1001 in bits 1 and 0. So I just shifted that up 8 bits, and I'm now here locating that at a proper EEPROM address. Then we have that whole block with the 3 16-bit words of the MLX ID 0, 1, and 2 at the addresses 12, 14, 16. Then comes a 16-bit of freely used memory, free A I called it, at address 18, 20, undocumented, we just saw that. Then there is that 16-bit K alpha at 22 and K beta parameter at 24. Then we have here 2 parameters in one word, the auth B1, B2, and another byte of freely usable memory at address 26. So by bits 7 to 0 is that parameter, and bits 15 to 8 are that free byte we can use. So first byte parameter, second byte free to use. Then we have another free byte, free C, and an F hysteresis parameter at 28, same game. First byte is free C, second byte is that hysteresis parameter, and I mentioned it already. We will go in detail over all these parameters when we really use them. Address 30, undocumented, address 2A, contains several parameters, map XYZ and 3D and filter. First 3 bits, maps XYZ, that's basically the 3D orientation to the device relative to the magnet. Then a 3D is just a Boolean, yes, no. And filter is also a 2-bit parameter. And then the rest undocumented again, like the next address 2C, which is also undocumented. And then we have our virtual gain, minimum, maximum. This is at address 2E, 1 byte for minimum virtual gain and 1 byte for maximum virtual gain. We talked or saw this virtual gain parameter already live in action when we did those get stuff of magnetic data. Card here, link in the description. KT, 16-bit parameter at address 30. Then we talked about that already in detail. The SM, ISM and select SM, ISM at address 32. So 15 bits for that float parameter it was, and 15 bits just for a Boolean. Then addresses 34 to 38, completely undocumented. And then we have the user ID, 2 times 16-bit in 3A and 3C. And we have, again, 1 freely usable byte in the word 3E. But yeah, only the first byte of the word. The second byte is, again, undocumented. Yeah. How can we retrieve that configuration information from the EEPROM? The answer is with the other memory read MOSI message, opcode 01, which gets as a reply in the next SPI transaction a memory answer MISO other message, opcode hexadecimal 02. The memory read MOSI message contains, besides the usual stuff, that is a CRC, the 2-bit marker, and the 6-bit opcode, which is, yeah, 2 16-bit addresses. So we can read 2 16-bit words from memory at once. And it can not only read 16-bit words from the EEPROM, but also from the ROM and the RAM, which is pretty useless for us because only the EEPROM addresses I've shown you are actually documented. We don't know what's located here at the RAM addresses or the ROM addresses. Why? 2 speculations for my part here. The first one is for testing reasons in the factory when the chip is produced. Second, it would have been too much trouble to filter here for specific addresses and give back an extra error message if you try to retrieve data from an undocumented address. But that's only my guess. The memory read MISO message contains, again, besides the usual stuff, 2 16-bit words. That is the data content at the 2 addresses we provided in the memory read MOSI message. Please note, the addresses we pass in the memory read MOSI message may be valid or not. In case of invalidity, memory read returns the data word 0. That supports my theory that we really couldn't be bothered to implement any code to check the validity of the addresses. The implementation is straightforward. First, we add the memory read MISOOpcode to our private, don't forget it, we moved that, to our private enum class MISOOpcode, and to our public enum class received. We add 3 public methods, the first being a Boolean here, a send memory read, which sends, of course, the memory read MOSI message and gets us an argument, an address 0, and a second address 1. While the second and third new public methods, last memory read data 0 and last memory read data 1, return us the 2 16-bit words contained in the memory read MISO message. As so often before, we add a struct memory read to our typedef union MOSI message, which contains the 2 addresses, address 0 and address 1, at the bytes 0 and 1, respectively 2 and 3. Finally, we also add a new struct to our type-def union MISO message. That is, of course, the struct memory read. This time it contains two 16-bit words, data 0 and data 1, the data we get returned in the MISO message, located again at the bytes 0, 1, respectively 2 and 3. In the CPP file, we first, so we don't forget it, add the new MISOOpcode memory read to the MISOOpcodes array in our private valid marker opcode method. The implementation of our public method sendMemoryRead is due to our ingenious library framework we have here. Sorry. Quite easy. So we create here a new local variable MOSI message with the marker other and the MOSI opcode memory read. And then we fill here in our MOSI message memory read address 0, the address 0, and in address 1, address 1. And then we send the whole MOSI message. Equally trivial, the implementation of last memory read data 0 and data 1. We just return MISO message memory read data 0, respectively MISO message memory read data 1. In the sketch itself, I've extended our serial print MLX90363 last function here with another case statement inside the switch. And that case statement is, of course, for received memory read and just prints out the two 16-bit words we can get with the last memory read data 0 and data 1 as hexadecimal numbers, because that's easier to read for us. In the loop, we have now 8 identical blocks. Each block is calling, of course, a sendMemoryRead with different addresses here from our enum address, handles an error if some occurs, and otherwise does a serial print MLX90363, which should, in theory, return a last memory read message. Remember, not with the addresses we just requested, but with the addresses we requested before. So since this is a loop, we have here the block 1, a sendMemoryRead for pin filter and the MLX ID 0. And we should get that back in the second block here. While the second block itself, of course, sends MLX ID 1 and MLX ID 2, and then a free A and key alpha, and so on until we come to our last pair of addresses. So we have 16 documented addresses in total. User ID 1 and a free D, which will be returned, not here directly. Here we have the 7th block data returned, but again, because it's a loop, at the very beginning. That is, here we get from our 8th block the data returned. That's it. And that's how the whole thing looks in the serial monitor. So we have here our block 1, one of many we're looping. So we do here the sendMemoryRead for pin filter and MLX ID 0, but we get back, from the end of our loop, the last memory read for user ID 1 and free D. Please note, user ID 1 is 3. And then we repeat the whole stuff here 8 times, as you know. And interesting here, block 7, we send a request for SMISM, cell SMISM, and user ID 0. And we get back as user ID 0 a 1. Take note of that. User ID 1 was 3 and user ID 0 is 1. And according to the datasheet, The default value for the user ID words here is for the first word, which I call user ID 0, 1, and for the second word, which I call user ID 1, 3. So we must be doing something right. However, these hexadecimal values don't get us anywhere. So we need to dig a little bit deeper. That's it for today. Yeah, we better take a break right now because the next step, that is decoding all these bits, bytes and words in the configuration, that will take probably another half hour. So yeah, a shorter video in between is okay, I think. Anyway, that will be what we will be doing next time. We will decode all these bits and have a little bit closer look at the different parameters. Not only those that are mentioned here in chapter 15, but also that are hidden further down in the data sheet. I will do my due diligence this time and not rely on just one chapter of the datasheet, assuming, yeah, this will be a complete list. I mean, why shouldn't that be a complete list? Yeah, reasons, huh? Okay, till next time, bye.